Impulse graph. Graphs are powerful tools to help solve physics problems. So far, we've dealt with a constant force exerted over a given time interval. But forces are not always constant. Most of the time, they are changing over time. In the baseball example, the force of the bat starts out very small as it makes initial contact with the ball. It then rapidly rises to its maximum value, then decreases as the ball leaves the bat. This would be a very difficult problem to solve without a graph. Start with representing a constant force over a time interval delta t and plot force versus time on a graph. So here's our force versus time graph. And we have a constant force represented here, and we have a certain time that the force is being exerted. The area under that curve is the impulse, or change in momentum. Why is that? Well, the area, it's a rectangle, is just going to be height times base, so that's F delta t. And what is F delta t? It's impulse. It is also the change in momentum. Now, for areas above the axis, above the time axis here, we're used to calling that the x-axis. In this case, it's just time. Assign a positive value for the impulse. That means you have a positive force. For areas below the x-axis, assign a negative value for the impulse. By taking the area under a force time graph, we have found both impulse and delta p, change in momentum. If the force is not constant, the area can be found by breaking it into solvable shapes, such as rectangles and triangles, and summing them up. Now let's plot a momentum time graph. And we get a straight line. And what is that straight line equal to? Well, let's find the slope of it. It's rise over run, or delta y over delta x, or in this case, the change in momentum over the change in time. And what is that? Well, that's the net force that's acting on the system, or your object. So because F delta t is equal to delta p, right? So you have delta p over delta t equals force net, and then multiply both sides, and you get F net delta t equals change in momentum, the impulse momentum equation. A 2 kilogram object at rest experiences a net horizontal force in the positive x direction and begins moving. Use the force time graph below to find the net impulse delivered by the force after it has been applied for 6 seconds. Now what do we notice here? The force is changing, right? Starts at 0, goes up to 2 newtons, stays at 2 newtons for a while, then decreases. It always is a positive force because it's above the time axis. To find the impulse, we need the area under the curve. I know it's just straight lines and it's not curving at all, but in physics we call that a curve. If you can recognize that it's a trapezoid, you can use the trapezoid area equation, which is 1/2 times base 1, here's base 1, plus base 2 times the height of your trapezoid. So that's 1/2. Here we have 6 seconds. Over here, this distance here is 2 seconds. And then the height of this is the 2 newtons. So we put all those numbers in, and we get an impulse of 8 newton seconds. But what if you don't know the trapezoid formula? Well, we'll divide this up into 3 little sections. Section 1 here is a right triangle, section 3 is a right triangle, and section 2 is a rectangle, pretty close to a square. So what we're going to do is find the area of number 1 here, and the area of a triangle, of course, is 1/2 times base times height. So it's 1/2 times 2 seconds times 2 newtons, and we get 2 newton seconds. We then go for area 2. That's going to be height times base, so that's 2 seconds times 2 newtons, 4 newton seconds. And finally we have 3, and it's got the same geometry, just reversed a little bit, same numbers, and we get 2 newton seconds. We then add all 3 of them together, and we get the same answer as the trapezoid. 8 newton seconds is the impulse after 6 seconds have gone by. Now we have another 2 kilogram object, starts at rest. It experiences a net horizontal force in the x direction and begins moving. Use this force time graph to find the net impulse delivered by the force after it has been applied for 6 seconds. This time we'll divide the total area into two triangles to find the area under the curve. And in this case, when we talk about area under the curve and your shape is below, you're really just talking about the distance between it and your time axis. So the first one here, first impulse is 1/2 times base, which is 3 seconds, times the height, which is 2 newtons because it's a triangle, 1/2 base times height, and we get 3 newtons per second. Now, somewhat of a trick is down here. You still have the same base and the same height, but it's in a negative direction. You are exerting a negative force, so you'll have a negative impulse. So that's negative 3 newtons per second. We then add the two of them together, so you get 3 plus or minus 3, and you get 0 impulse after 6 seconds.